Alright, welcome back. This video about the Gauss-Jordan method is going to be cut into two parts. So first I want to talk about what the Gauss-Jordan method is, where it comes from, and why it works. And then in the second part we're going to open up Sage, and we're going to have Sage determine whether or not some matrices are invertible using the Gauss-Jordan method. So let's go ahead and get started with the first part. So we see here the Gauss-Jordan method. It says first step you want to join I, then you want to row reduce, and if you get the identity matrix in the first half, then your matrix is invertible and you can exactly read off what the inverse is. So our first step here, we want to create this thing, then we want to row reduce to this thing, and if we get the identity matrix, then A is invertible. Alright. So, how does this work? Let's go ahead and look at this through the lens of an example. So the example I want to look at is, let's take A to be 1, 0, 2, 1. So something super easy. We're going to be able to find the inverse very quickly using the Gauss-Jordan method, but before that, let's think about why we're doing this. So, if A is invertible, we get something that looks like A times a matrix equals the identity. So let's write that out as A times A, B, C, D, corresponding to the entries of the inverse, equals 1, 0, 0, 1. And now we want to actually go back to how matrix multiplication is defined. So in order to get the first column of the output, the identity matrix, out of the product, we're going to take the rows of A and multiply it by the first column of the inverse. So in particular, what that means is that if we look only at our first column, we want A times AC to equal 1, 0. Right. But now, what this looks like to me is it looks a whole lot like a linear system of equations like we were doing in section 2.1. A is our matrix, little a and c are our variables, and then 1 and 0 are our constant. So we can then turn this into, let's stick A in the beginning and 1, 0. And in order to find the AC, the first column of our inverse, we just have to row reduce this and solve for A and C, the variables. So our row reducing we'll do is we'll take row 2 minus 2 row 1 and turn that to the new row 2. So we get 1, 0, 1. Our row 1 stays the same, and row 2 becomes 0, 1, negative 2. Right. So this tells us this right here at the end, this is the first column of our inverse. So first column of A inverse, because we know that from this A equals 1 and C equals negative 2. Just from going back to chapter 1 or 2.1 and remembering what happens when we row reduce a matrix. So if we do the same thing with the second column, we get that A times BD has to equal 0, 1. Okay, so again we turn that into our matrix, our augmented matrix, 0, 1. And the wonderful thing is that we're going to do exactly the same process of row reducing that we did the first time around. We're going to replace row 2 with row 2 minus 2 row 1s. So we get a 0, 1 there for our second column of A inverse. So again, here's our, oopsies, our second column of A inverse. because we read off that b equals 0 and d equals 1. Right. So that's wonderful. We've turned this question of finding inverses into a question of systems of linear equations. Let's go one step further, and we did the same elementary row operations in both cases. So why not just compactify that into a single step? All right, let's take the same augmenting 1, 0, 2, 1, but now let's augment with both of those columns because they're not going to interact with each other. So we're still going to do row 2 minus 2 row 1 becomes row 2 to row reduce A to the identity matrix. And now these two columns over here of the identity matrix that we augmented by aren't going to affect each other when they row reduce. So ultimately, we do get the same thing that we got looking at the first and second column, but now we've just compactified our work and made our lives easier. So this right here, this is our A inverse. All right, so that should be super awesome. All right, so that is the writing I'm going to do. Now I'm going to open up Sage and show you two examples of using the Gauss-Jordan method to find an inverse if it exists. All right, let me show you how to use the Gauss-Jordan method in Sage, actually. So on our computers in the classrooms, we have Sage 9.0 installed, so you can go ahead and open that up instead of having to use the cell server. So here I've opened it up using the Sage Notebook option. And once you're in the Sage Notebook option, you can move around to your files. You can create a new one by hitting the New button and hit Sage Math 9.0. If all you want to do is use Python, you can still do that as well. Alright, so let me show you what a notebook looks like. So I open this one that I've created, and we have some text followed by some code chunks. So here, in example 1, I want to use the Gauss-Jordan method to find the inverse for this matrix below. So I've already put in the Sage code, so you don't have to listen to me type. And so let's go ahead and execute that. So I can either press Shift and Enter, or I can press this Run button up here. All right, and so A is saved as the matrix we expect it to be. And then the Gauss-Jordan method says augment your matrix A by the identity matrix, properly sized. So that is what we're going to do in this next code chunk, and then we'll print that out to see what it looks like. So I run that. All right, and we notice we have our matrix A augmented by the identity matrix. So let me just go ahead and add within this code chunk that I want to print out AI, the reduced row echelon form. Let's see what that looks like. All right, so we see here we have the identity matrix coming first, and then the last four columns are going to be our matrix that is the inverse of A. So if we want to test that out, we could insert a new code chunk or new cell. Oh, I meant to say below, but we're going above. All right, and we expect A inverse to be the matrix. All right, so I've got that all typed in. And now let's go ahead and test that this is indeed the inverse. So let's print what it looks like if A is multiplied by A inverse. Right, and look, we did indeed get the identity like we expected. Alrighty, so then let's go on and do another example. So here's another random 4x4 matrix. Let's test to see if it's invertible using all of the same steps above. Alright. And we see here, now that we've row reduced B augmented with the identity matrix, that the last row is 4 zeros. So we don't get the identity matrix in those first four columns. So what that tells me immediately is that B is not invertible. Which is a bummer. It's sad to not have non-invertible things, but it's a very quick and easy check to whether or not a matrix is invertible using this Gauss-Jordan method. Alright, so if you want to use Sage in the future to do this, I again recommend doing so. It makes it quick and easy to input a matrix, augment, and row reduce. Let me know if you have any questions. Enjoy!